Hello! This is the second video in our series on mathematical problem solving. If you haven't checked out the first video, make sure to do so. I've linked it in the cards above because this video follows straight on from that one. In the previous video, I talked about 5 general problem solving techniques. They were get your hands dirty, make conjectures, draw pictures, restate the problem, and work backwards. And I also gave you 3 problems where you could try out some or perhaps all of these different techniques. Problem 1. Cutting chocolate. The first problem was to find the fewest number of straight cuts needed to break up a 3 by 5 bar of chocolate into 15 pieces. The best way to start this problem is to get your hands dirty, literally for preference, but you can draw pictures if you don't have any chocolate to hand. Here I have got 3 bars of chocolate and we're just going to try out different ways of cutting them up. So perhaps an obvious way would be along like that and then along like that. So 1, 2, 3, 4, and now I need to cut each of these individually. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So it took 14 cuts like that, but we don't know if that's the best we could do. Maybe we chose the wrong pattern. Tasty. So let's try cutting it this way first and then that way. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's interesting. We've got 14 cuts again. So we've tried sort of horizontally and then vertically. We've tried vertically and then horizontally. Let me just try something slightly random. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 and 14. I did 2 at once there. So 14, again, each way gave us 14 different cuts. This might lead us to conjecture that the fewest number of cuts required is 14. How might we prove that this is the correct answer? A useful trick is to turn the question on its head. Instead of asking how many cuts are needed to get 15 pieces, we could ask how many pieces we have after some number of cuts. Each time we make a cut, we start with 1 piece of chocolate and finish with 2 pieces. In other words, we increase the number of pieces of chocolate by 1. If we start with 1 chocolate bar, after 14 cuts we will have increased the number of pieces to 15. So our conjecture was correct. Notice that it doesn't matter what cuts we choose to make and in what order. However we choose to cut up the chocolate, we will necessarily break it up into individual squares after 14 cuts. Thinking about the geometry of the problem was in fact a red herring. This way of thinking about the problem also allows us to generalize very easily. If we had an m by n bar of chocolate that we wanted to cut up into m times n pieces, it would take exactly m times n minus 1 cuts. Problem 2. A busy bee. The second problem was about finding the shortest path from one corner of a beehive to the opposite corner whilst crawling along the inside walls of the hive. The first thing we want to do is restate the problem, not drastically, but just to get rid of the unnecessary information. We can think of the hive as a cuboid with dimensions x, y, and z. Then our question is, what is the shortest path along the surface of the cuboid from one corner to the opposite corner? We may as well assume that we have chosen to label the dimensions such that x is less than or equal to y, which is less than or equal to z. We can now try out some different possible paths. For example, we could try going along the edges of the cuboid. This path has a length of x plus y plus z, but it's clearly not the shortest. For example, we could take a shortcut across one of the faces. Maybe this is the shortest, but how can we know for sure? It is at this point that a well-chosen picture works wonders. Notice that as the path crosses over an edge or a corner of the cuboid, this doesn't add anything to the total length of the path. From the point of view of the problem, the corners and edges are irrelevant. If we can picture the surface of the cuboid as completely flat, this should make the problem clearer. The obvious way to do that is using a net. If we mark the start and end points on the net, then the shortest path becomes obvious. We just need to join them by a straight line. But this is where we need to be wary of the treachery of images. There are, in fact, 3 different ways we could have drawn the net, and each way gives us a different path with a different length. We can compute the lengths of these paths using Pythagoras' theorem. Together with our convention that x is less than or equal to y, which is less than or equal to z, you can easily check that the shortest path is actually the one in the middle. We can visualize all 3 of these paths on the cuboid. Problem 3. Hilbert's hotel hunt. The final problem I gave you last time concerned Hilbert's hotel hospitality hassle. Remember that he had an infinite number of bookings, and the guests in the nth booking would only stay in the rooms numbered by multiples of n. His guests are unscrupulous, and so if they found money left by the previous occupant of the room, they would take it and leave without paying. Otherwise, they would leave the money for their stay on their bed. The question was, when all the guests have left, which rooms will contain money? At first, the pattern of where money is, after some number of days has passed, looks quite chaotic. But notice that after the first night, no guest ever checks into room 1. After the second night, no guest checks into room 2. After the third night, no guest checks into room 3, and so on. So a stable pattern should eventually emerge. As with the other 2 problems, perhaps a natural place to start is just to see what happens over the first few nights, and see if we can spot a pattern. This table shows if there's money in each room after each of the first few nights. I have circled when we know that a room is not going to change whether or not it contains money anymore. After the first 8 nights, we can see that only rooms 1 and 4 will definitely contain money at the end, but that doesn't clearly indicate what the pattern is. What if we work backwards instead? Suppose that after all of the guests have checked out, the room numbered R has money left in it. Then what can we say? Well, it must have had an odd number of guests stay in it, because if there had been an even number of guests, each time a guest left money in the room, the next guest would have taken it again. How can we count how many guests stayed in room R? On the nth night, a guest stays in room R if and only if R is a multiple of n, or, put another way, if and only if n is a factor of R. Therefore, there will be money left in room R if and only if R has an odd number of factors. This means that we can restate the problem. Asking which rooms Hilbert has to look in to find his money is equivalent to asking which rooms have numbers with an odd number of factors. This question is relatively straightforward to answer. Normally, a number's factors come in pairs. For example, 10 is 1 times 10 or 2 times 5. 15 is 3 times 5 or 1 times 15. The only time this is not the case is when a number has a repeated factor. So, for example, 9 is 1 times 9, but it is also 3 times 3. So the only numbers with an odd number of factors are the square numbers. So Hilbert should only look in the rooms whose numbers are squares. Square numbers seem quite sparse among all the positive integers, so you may worry that Hilbert has been ripped off by all his thieving customers. But worry not. He's actually made exactly the same amount of money as he would have done if his guests had been honest. If you want to find out why, you should look into what else has been happening in Hilbert's hotel. That finishes us off for general problem-solving techniques. It's important to remember that there are usually several ways of approaching a problem. So if you solved any of these problems using a different method, let me know in the comments below. I'll be very interested to read them. From now on, we are going to focus on specific problem-solving techniques. Each one will have several videos with lots of problems for you to try. In the next video, we're going to start looking at techniques from game theory. In the meantime, here's another problem to think about. In a game of 21 dares between two people, the object is to count from 1 up to 21, with each player taking it in turns to say the next 1, 2, or 3 numbers. The player who says 21 loses. Here's my question. Is it better to go first or second? And is there a strategy to win? If you've worked that out, what about if you're playing a game of P dares, where you have to count up to P instead of up to 21? Also, what if you're allowed to count up to the next Q numbers on each turn, rather than just the next 3 numbers? Thank you for watching. Don't forget to put your solutions and ideas in the comments down below, and subscribe to be notified when we release the next video on mathematical problem solving. See you then.